Our third topic is called as moment distribution method. Okay, this is a method to analyze statically indeterminate beam and frames. This method was developed by Hardy Cross in 1930, and it has been recognized as one of the most notable advances in structural analysis during the 20th century. Essentially, the method begins by assuming each joint of a structure is fixed. Then by unlocking and locking each joint in succession, the internal moment at the joint are distributed and balanced until the joint have rotated to their final or nearly final positions. It will be found that this process of calculation is both repetitive and easy to apply. Before explaining the technique of moment distribution, however, certain definition and concept must be presented. For moment distribution method, students should understand some important terms and concept. Number one, sign convention. Bear in your mind, every time we want to analyze any type of structures, any type of beam and frame using moment distribution method, we have to set our mind like this. Clockwise moment that act on the member are considered positive. What does it mean? Let's look at this. Let's say we have a continuous beam A, B, C, and D. If I want to draw the free body diagram of this beam, I have three members. A, B, member AB, member BC, and member CD. Member and moment or internal moment that act on the member are considered clockwise positive, means like this. The red arrow shows the member and moment. Member and moment. And it is clockwise. Positive. As the first assumption that we need to make. Okay. Beside member and moment, we also have joint moment. What is joint moment? What is joint moment? Let's look at this. Let's look at this. Joint A is fixed. A is fixed. Joint B, joint C, roller. Joint C is roller. Is fixed. B is fixed. And please remember that for joint moment, it is always opposite with member and moment. So opposite with member and moment MAB is this. Opposite with member and moment MBA is and this, and this, and this, and this. Okay, all this is okay. This is MAB, this is MBA, this is MBC, this is MCB, this is MCD, and MDC. Alright, so actually the value that we will calculate using moment distribution method is member and moment. Okay, the next term that is quite important in a moment distribution method, it is called as member and moment. Sorry, fixed and moment. Fixed and moment. Before that, I want to highlight this first. Moment at roller MB A plus MBC is equal to 0, because MB is equal to 0 due to the roller support. Same occurs to joint C, where MCB plus MCD is equal to 0, because MC is equal to 0 due to the support. However, for this one, this is fixed and this is fixed, and for fixed, moment is not equal to 0. Not equal to 0. Okay, for fixed and moment, I have explained to you earlier that for fixed and moment, it is actually represent behavior. It is behavior. For example, okay, fixed and moment means both end is fixed. When subjected to loading, what happen is the beam will deflect. The beam will deflect. So the deflection of beam is the behavior. So the fixed end moment will occur at both fixed end to counter back the bending beam. Okay, to counter back, we have to apply moment at both end like this, so that the bend beam will go back to straight position. Straight position. Straight position. That is fixed end moment. And fixed end moment also, actually fixed end moment can be divided into two conditions. One is due to external load, and another one is due to delta. And delta in moment distribution method can be distributed into two for beam It is normally due to support settlement. And for frame, commonly it is due to side sway. Common. So this is common one. Common. Okay. Okay, I want to introduce you to number 2. This is number 1, this is number 2. Due to deflection. Okay, let's say consider beam like this. Okay, the beam has been pushed to new position due to delta. Okay, so original is horizontal. This is original position, and this is new position. Due to delta, the beam is pushed to rotate clockwise. And this angle is called as chord rotation. And for chord rotation, we need to measure the angle from original position to new position. Why we need to do that? Because we want to identify the fixed end moment occur at both A and B. Okay, if the behavior like this due to delta, and the beam want to be straight again, what we need to do, we need to apply moment to counter back so that the beam will go back to straight position. Okay, so to push this point and this point to straight position, we need to apply moment like this. Then only the beam will go to straight position again. And this direction is fixed and moment. And I can say that when angle is clockwise, FEM is counter clockwise. Angle and FEM must be opposite condition. Same goes to column. If we have, let's say, like this, column due to delta, column move to this, okay, this one to this one, the moment will push this to straight position, push this one also, so, and then the beam will go to straight position again. If we measure the angle, original, new, the chord rotation is clockwise and the FEM is counterclockwise. Okay, I repeat again on the fixed end moment. Remember that fixed end moment is the behavior. Okay, let's say the beam, the fixed ended beam has loaded with UDL. The bend due to the external loading will bend, and fixed end moment will push both ends to straight position. Alright, and actually fixed end moment can occur due to two conditions. Number one is due to external load, and number two is due to deflection. And for common cases, we analyze beam with support settlement, and we analyze frame with side sway, and both is delta. Alright, I want to explain further on FEM with delta. Okay, let's look at this diagram. Okay, here is the delta. The delta is vertical. The member is horizontal. Between delta and length of the member, it must be perpendicular. Okay, the original position of the beam is horizontal. The new position is this inclined member. Okay, what is the meaning of fixed end moment? Fixed end moment, the moment will push both end, and A and B will push both end, push this and push this, so that the inclined member will move to straight position again. Okay, we can measure the angle. The angle is called as chord rotation, and we measure the angle from original position to new position. What does it mean? For fixed end moment, angle and FEM must be opposite. opposite. Okay, let's look at one example of column. Okay, one example of column. Column is vertical member. Column is vertical member. Means that the delta is horizontal, because the member and the delta must be perpendicular. Okay, the incline is the new position. The angle is clockwise. The angle rotation, the angle is clockwise. So this is the new position of the beam of the column, the incline member. This is due to the delta or side sway condition. Okay, what happened is the moment or fixed end moment will push both sides, this and this, so that the column will move to straight position, which means vertical condition, original position again. So we need to apply moment at both end to push it back to original position. So what we can say is, when the angle is positive, FEM is negative. When angle is negative, FEM is positive. Okay. Okay, let's look at the next important term in moment distribution method. It is called as member stiffness factor. Member stiffness factor. Okay, for the member stiffness factor, okay, we need to consider far end condition. Okay, we have two condition. One is end fixed, and another one is end pin. And the formula is 4EI over L. For far end pin or roller, it is K equivalent to 3EI over L. Okay. Okay, next is joint stiffness factor. Joint stiffness factor is total K. Because remember that K or stiffness is for element. As we have discussed in chapter number 2, stiffness is for element. For moment distribution method, we need to determine the stiffness factor for each element, and then we have to join it together to determine joint stiffness factor. Why we need to have joint stiffness factor? Because we need to determine distribution factor, and to determine distribution factor, we need to have joint stiffness factor in order to determine internal moment, at each support of the beam. Okay, internal moment here is also called as member and moment. By looking at this figure, we are actually determining AB, member AB. We have also member BC and member CD. Member and moment means this. At the beginning, at the beginning, the moment that act on the member is clockwise, and this is MAB, MBA, MBC, MCB, MCD, MDC. So we are going to determine these 6 values, because these 6 values are called as member and moment or internal moment at each support. Okay, step number 1. Since there are 3 member AB, member BA, and member BC, member AB, member BC, and member CD. So we need to determine 3 stiffness factor. Remember that the stiffness is for element. Since we have 3 element, we have 3 member stiffness factor. Okay, for member AB, we have to refer to far end condition, because B is internal. So we need to look at to A. A is fixed, so we use the formula for far end fixed. It is 4EI over 12. Alright, for both internal support B and C, we need to use 4EI over L, because internal is assumed as fixed. And for member CD, the far end is referred to D, because C is internal, C is considered fixed, D is far end fixed, so we need to use 4EI over 8. After that, after we determine the stiffness factor, this is step number 1. After we determine the stiffness factor, we have to determine distribution factor. This is step number 2. Distribution factor. For distribution factor, it is equal to K divided by total K. K divided by total K. So for distribution factor, K and DF, we have AB, BA, BC, CB, CD, and DC. They are all 6. Alright. K in terms of EI is 4 divided by 12. Is 4 divided by 12. For member BC, it is 4 divided by 12 also. For CD, it is 4 divided by 8. So using this formula, using this formula, let's say we want to determine DF AB, it is equal to it is equal to K AB divided by total K at joint A. It is KAB plus infinity. So the value is 0. Why it is infinity? Because fixed end is not the end of the structure. We do not know the fixed connecting to infinity members, and we do not know the value. So it is infinity. The end of structures is either pin or roller or cantilever. If it is fixed end, means it is connecting to others. It is connecting to other member. So it is infinity. So we get 0 for member AB. So for AB and DC. Let's say we want to calculate a DF for BA. And for BA, it is KAB divided by KAB plus KB KBC, and it is 0.5, 0.5. Okay, let's look at this. Fixed end moment, we just have to apply the formula given, and the formula will also given to you during examination. Okay, for member AB, there is no external load, so the fixed end moment is 0.